everybody, and welcome to Lesson 2.4, Global Water Resources. The content in this video is aligned to the third edition of Environmental Science for AP and covers information from College Board Units 1.3, 4.6, 9.6, and 9.7. The last major system left to explore is the hydrosphere, our water resources. Without liquid water, life on Earth would never exist. Therefore, it is vital for us to understand where our resources are and how we use them. This leads us to the content objectives of understanding that ecosystems are the result of biotic and abiotic interactions. Earth's systems interact, resulting in a state of balance over time, and local and regional human activities can have impacts at the global level. At the end of this lesson, you should be able to identify the types of water resources available on Earth, describe the global distribution and principal environmental aspects of aquatic biomes, explain the importance and use of aquifers, describe the characteristics of a watershed, identify the parts of a river system, explain the importance of estuaries, explain the causes and effects of global ocean warming, explain the causes and effects of ocean acidification, and explain how water extraction for irrigation impacts water availability. This leads us to being able to answer our guiding question: how do we access water resources? Let's begin by looking at how water resources are distributed around the globe. We begin by categorizing water based on its relative salt content. Water with a high salt content is referred to as marine or saltwater. This is held largely in the world's oceans and makes up approximately 97% of the volume of water on Earth. Brackish water, or water that has a moderate amount of salt, is a mixture of marine and fresh water and makes up about 1% of resources. These are found where freshwater and saltwater bodies mix, such as where a river empties into an ocean. Lastly, there is freshwater, which has a very dilute salt content. The remaining 2 to 3% of the water on Earth is categorized as freshwater. This category of water is further broken down into 3 types based on their location: glaciers and ice caps, where 69% of the freshwater on Earth is found, groundwater, which makes up 30%, and surface water, which is the remaining 1%. Of surface water, most of it is found in polar areas where it is locked up in permafrost and other widely distributed ground ice. Lakes make up the next largest percentage of surface water, with the remaining volume coming in soil, swamps, marshes, and rivers. Aquatic biomes, also known as aquatic life zones, are determined based on their salt content. Therefore, they are identified based on the same categories of the overall water resources on the planet. Make note that estuaries form a very important part of the ecosystem and have one of the highest net primary productivity levels of all aquatic biomes. Only coral reef ecosystems have higher net primary productivity. Estuaries also form something known as an ecotone and produce an area where unique organisms are found. These areas are important for biodiversity and overall ecosystem stability, particularly in the fact that they provide regulating services like water filtration and flood control. Freshwater aquatic biomes are most likely going to be rivers, lakes, streams, and ponds. Some organisms do live in aquifers, but they are microscopic. Marine ecosystems include the open ocean and a very small number of saltwater marshes. Brackish water makes up the rest of them: estuaries, marshes, and swamps. Aside from glaciers and ice caps, the majority of our freshwater resources are held in what is known as an aquifer. This is a deposit of water beneath the ground that can be tapped into using wells. First, let's talk about the basic components of an aquifer. When water infiltrates into the ground, it will percolate as deep into the soil as possible until there are no more open spaces between the soil particles. This is known as the zone of saturation. The very top of the zone of saturation is known as the water table. Above the water table is the zone of aeration. In this area, there is still open space between soil particles that can be taken up by water. When discussing aquifers located at the water table, we call these unconfined aquifers. This means that their upper boundary is the surface of the ground. These kinds of aquifers can be tapped using a basic well with very little difficulty. However, some aquifers occur when water infiltrates and enters the space between two layers of rock, or confining layers. An aquifer such as this is known as a confined aquifer and can only be accessed using what is known as an artesian well, which requires more advanced machinery to break through the confining rock layers. Aquifers can be recharged or refilled through precipitation and additional infiltration. They are reduced, however, when they are overused for things such as irrigation and municipal water supply. One of the largest aquifers in the U.S., the Ogallala Aquifer, covers 8 Midwestern states and supplies irrigation water for the majority of the Great Plains area. However, recent shifts in climate, drought, and continued overuse have depleted this aquifer significantly. Another component to be familiar with is what is known as a watershed, or drainage basin. This is the geographic area, often defined by mountain ranges or shifts in elevation, from which all water drains into a central body, often a lake or a river. Watersheds are important as the conditions through which the water moves plays a key factor in determining its quality as it enters a lake or river and the amount of water that is actually taken up through infiltration. Aquifers and watersheds often go hand in hand. It is important to note that a single area can be part of one or more watersheds, depending on the identification of the central body of water and the geographic area being reviewed. Here, we see the major watersheds of the continental United States. Notice that the vast majority of the U.S. is taken up by the Mississippi River Basin, or the Mississippi River watershed. Water from the area between the Rocky Mountains and the Appalachian Mountains will eventually find its way into the Mississippi River and then into the Gulf of Mexico. Note that it is in this area where the Ogallala Aquifer resides. It is also the area of the biggest agricultural production for the United States. We can also take a step back and note that the Mississippi River watershed is made up of several smaller watersheds, such as those associated with the Missouri, Ohio, and Tennessee rivers. In the vast majority of cases, a watershed will collect all of the water into an area of a river. Let's take a moment to identify the parts of a river system. All rivers originate in a mountainous area of some kind. It doesn't have to be as large as the Rocky Mountains, but some elevation is required for this ecosystem to form. The place at which the river begins is known as its headwaters. This area is often fed by precipitation runoff and the melting of glaciers or snowpack. Headwaters are often very fast-flowing, but also relatively shallow. As the river moves downward in elevation, it meets the main body of the river, which is found in the floodplain. The floodplain is the area at which the river is very wide, but still moving relatively quickly. It is here that the river will overflow its banks during heavy rains, depositing silt and other nutrients that make floodplains ideal for agriculture. However, it also makes them dangerous for construction. Within the floodplain, several smaller rivers and streams, known as tributaries, may come together to join the larger body of water. The point at which one or more rivers meet is known as a confluence. A single river or river system may have many tributaries and many different areas of confluence. Lastly, there is the mouth of the river, where it empties into another body of water. This is often a lake or the ocean. At the mouth, the river is wide, shallow, and slow-moving. This leads to the deposition of sediment deposits that form what are known as deltas. If the river empties into a body of salt water, the mouth of the river can form what is known as an estuary. Estuaries and deltas are often confused, but they are not the same thing. Deltas refer to the deposition of sediment at the location where two bodies of water meet. Deltas can be ecosystems and habitats for a variety of organisms. Estuaries, on the other hand, are the areas of the mixing of fresh and salt water. In short, a delta refers to the sediment. The estuary refers to the water. Remember that estuaries have very unique ecosystems due to the overlap of fresh and salt water, forming what is known as an ecotone, and have a very high net primary productivity for aquatic biomes. Now that we understand how our water resources are distributed across the planet, it's important for us to look at the ways in which we make use of these resources and how that use impacts the hydrosphere and its systems as a whole. Taken globally, the vast majority of water is used for agricultural purposes. While part of this is due to the need for irrigation for large amounts of crops and for providing animals with much needed water, it is also due to the fact that the majority of water use methods in agriculture are incredibly inefficient. This leads to massive water loss, greatly inflating the overall use of water for the process. Next is industry, where water is used as a lubricant for machinery and throughout the manufacturing process. Make note that industrial use also includes energy production processes, where water is boiled to produce steam. Lastly, there is municipal, or use in individual homes and small businesses. This is the usage of water in bathrooms, kitchen, outdoors, and for cooking and drinking. The graph on the right shows a different view of the uses of water by humans. Note that our total water withdrawal has been increasing steadily since 1900, with a sharp increase beginning in the mid-1950s. It is interesting that this coincides with the first Green Revolution, which sought to increase the yield of a variety of agricultural products. Beyond large-scale water use, human activity also greatly impacts the oceans in terms of volume and temperature. As we've seen before, increased global temperature leads to the melting of ice and snow at the polar ice caps, which play a crucial role in reflecting incoming solar radiation. When this reflecting ability, the albedo, is reduced, water absorbs more energy, and the overall average temperature of the ocean increases. The increase is not uniform, with greater changes felt at the polar regions rather than at the equator. Beyond the addition of literally more water from these melting ice caps, this increase in ocean temperature leads to what is known as thermal expansion, where the molecules of water that make up the ocean move further away from one another. Thermal expansion, in addition to the melting of land-based ice, leads to rising sea levels. In addition to causing an increase in sea level, this increase in heat in the oceans can lead to drastic changes in ecosystems, leaving organisms in water that is far warmer than the conditions to which they have adapted. This is one of the causes of coral bleaching, where coral reefs lose their symbiotic organisms, leading to them losing their color and their ability to go through basic life-sustaining processes. Since 1880, sea levels have risen approximately 8 to 9 inches, or 20 to 23 centimeters. This increase in sea level is seen and felt most extremely along coastal areas. In general, for every 2.5 centimeter rise in sea level, an average of 2.5 meters of beach or other coastal area is lost. This translates to the loss of approximately 22.5 meters of coastal area in the last 140 years. To put this into perspective, the map shows the coast of North Carolina as it exists today, outlined in blue. A 1 foot or 30.5 centimeter increase in sea level along the North Carolina coast would completely flood up to around 93 miles. In short, Fayetteville would become beachfront property. Another cause of coral bleaching is ocean acidification, which we discussed briefly when we discussed the carbon cycle. In addition to causing more acidic water that reduces the symbiotic interactions between coral and their bacteria, acidification of the oceans removes carbon dioxide from the water that otherwise could be incorporated into calcium carbonate, which is the basic structure of coral and other shelled organisms in the water. Make note that while the drop in pH is not incredibly drastic, Such a shift can have very dramatic effects across the ocean and in ecosystems that are the most sensitive and the most vulnerable. The following slide provides you with an opportunity to see how some of these ideas are connected together. Feel free to pause the video and explore the connections between these topics. Then use the statements at the beginning to review.